I bet you guys thought I was going to forget to send you this screencast, suckers. So today I'm going to be talking about cloning, the concept of cloning. And I wonder if there's a way I can make this fatter. Oh, I can. Oh, yeah, hold on. Let me erase that. Cloning. That's not fatter. Oh, well. Guess it's good enough. And this type of cloning I'm going to be talking about is actually the old version of cloning. And by old, I mean this is cloning that was done back in the 1960s. So you should keep in mind that the concept of cloning organisms isn't really all that new. I mean, relatively speaking, it's new. But it's not as modern, I think, as most people realize. And that's because most people get it confused with the new method of cloning that's happening, and that was developed fairly recently, within the past 15 to 20 years. All right, so old cloning. To understand this concept, we sort of need to we need to go back and think about cell biology here. Don't forget that every single one of your cells contains DNA inside the nucleus here. And what's kind of cool about this is that the DNA, let's say that this is a liver cell that we have here, and that next to it, let's see if I can make a copy of this thing. Oh, baby. Oh, I love it. Love it. This is a good screencasting. This makes me very happy. And let's say that instead of being a liver cell, this happens to be a nerve cell. Okay? What's interesting about this is that despite the fact that obviously liver and nerve cells do very different things, they both contain exactly the same DNA. Now, that's a little odd to think about because clearly one of them does the liver stuff and one of them does the nerve cell stuff. Yet somehow a liver cell knows to only look at the instructions in the DNA that tell it how to become a good liver cell, and the same thing can be said for a nerve cell. But ultimately what that means is the instructions are being ignored. They're still there, but the instructions are being ignored by a liver cell for what it means to be a nerve cell and vice versa. Okay? Ultimately, the implication of this is that any one of your cells contains all the information that's necessary to make another you. Whoa, that's kind of amazing. However, when you get to this point where you have a liver and a nerve cell, these cells are what are called fully differentiated cells. So let me pop that onto the next page here. This concept of differentiation. You have to call who, Rabbit?
Should I?
Okay.
Should I close the door?
No, it's okay. Differentiation. And differentiation is when cells become specialized. Now you might say to yourself, well, that means there's a moment where they're not specialized, and indeed that is the case. Because if we take this situation, let's say we have daddy's sperm come together with mommy's egg. Okay, so we have sperm here, we have egg going on here, and boom, voila, these two come together, right? And as a result, you form that combination, the first, what's called zygote. Zygote, which is the first cell, the first fertilized cell, which contains the nucleus. Now, at this point, this cell is completely unspecialized, and it has to be completely unspecialized. We have a better word for that concept of being unspecialized, however. The word is called pluripotent. Pluripotent. And pluripotent essentially means pluri meaning many, and potent means potential. Okay? So it has the potential to be very many different types of cells. But initially, that's all it is just a single cell all by itself. So, let's see. If I were to take a look at this zygote, you could imagine that eventually the zygote's going to become maybe a skin cell. Okay? But it could also become a nerve cell. And it could become a cell that lines your gut. Any number of these things. So the problem is, you say to yourself, well, gee, if it becomes a skin cell, then you're just going to be a big pile of skin. Well, that's exactly right. So in fact, what has to first happen, let me give us a new page here, is that if I start with this zygote, eventually this zygote actually divides in two. So you end up with two cells. And it undergoes DNA replication before that, so that both cells contain the exact same DNA. And then those divide into four, and those all each divide. So eventually you could imagine after a period of time, if this is time 0, this is after a couple hours, and this is after more hours than that. Eventually, ... you could imagine after many days, you would have a whole ball of cells. Each of them would contain the DNA that the other cells contain, identical copies of DNA. But once again, every single one of the cells in this what's called a blastula, okay, that's the name of that structure there, a ball of cells. Every single one of those cells in the blastula, while definitely it contains the same DNA, okay, same exact DNA there, they're all clones when it comes to cells of each other. They're also, every single one of them right there is pluripotent. Okay, all the cells are pluripotent. So no specialization has taken place. Now, what's kind of cool about this, and it's way beyond the scope of what we're going to discuss right now, but there are a whole bunch of factors that cascade down on top of this ball of cells. All right, I'm going to abbreviate factors with capital F's here. And what these factors do is they're essentially chemicals and proteins, all sorts of things, is they will affect a certain group of cells. So the cells that I just circled up in red will do one thing, and then another set of factors will affect those cells, and yet we have another set of factors affecting these cells. And these factors are what are responsible for steering a certain cell, or a set of cells, towards a certain specialization. So they become differentiated as a result of those factors. What's more is if I go back to what we had here, understand that these factors that I'm referring to are all contained in the egg. You have no factors, none of them here in the sperm. The sperm is really kind of cheap. All it does is have a whole bunch of, I just realized that you may not be able to see this, so let's see. I'm going to unlock. There you go. I just put a little X over the sperm there, and I also added some random lines that I didn't mean to do. Oh well, pretend they aren't there. So those factors exist, and those factors are what are ultimately going to lead to the specialization or differentiation of those cells, and eventually, voila, we have a human being. It took me forever to find. It's lame. All right? So, anyway, the bottom line is that if you were to do something tricky here, you could actually get a clone out of this deal. Wait, let me back up a bit. Of course, we understand that this blastula that I'm talking about here, if it is going to continue to grow into this, then it has to actually develop in the womb of its mother. Otherwise, it's going to crash and burn. So we always have to make sure that we implant this ball of cells into the right environment for it to continue to grow and develop, differentiate, etc. Now, imagine this situation. Imagine you have this ball of cells. Let me just pause it for a moment while I make my ball of cells. Okay, so there's my ball of cells. And I'm about to go, let's say that I actually have a special scope and tools that allow me to go inside a woman's uterus and check out this ball of cells sitting here implanted on the endometrium, the wall of the uterus. And I decide, you know what I'm going to do? I'm going to go after this cell right here, and I'm going to pluck it free. Okay? So I'm going to cut it away from the rest of those cells and carry it off. So I take this nice little cell. Don't forget, it's pluripotent at this point. It hasn't actually differentiated yet, so this is fairly early in the embryonic development of the organism. And I decide to go plant this into the uterus of a donor, or not a donor, I'm sorry, of a surrogate mother. Now, what's going to happen there is pretty amazing that once that goes in the uterus of the donor, and why do I keep saying donor? I hate myself. I don't mean donor, I mean surrogate mother. Okay? So it goes into the womb of the surrogate mother, and it then also starts to divide, and eventually, as long as there are resources available to it, you could imagine that it's going to divide to the point. In fact, I'm going to erase all this. I'm going to be cheating a little bit here. I'm going to go back over, and I'm going to make a copy of this right here. Copy it. Scooch over here. Paste my baby over here. Oh, that was lousy. Pretend the green's not there. Yeah, I don't see green. Do you see green? I don't see green. And ultimately, it would grow into a ball of cells. And don't forget that all the DNA that's hanging out over here and over in here, remember these two are the same, and this is the same as this one, which is the same as this one. All the DNA is, well, guess what? If I plucked this cell out here, it will also give rise to a whole bunch of cells that contain that same exact DNA. So that after 9 months of gestation, the child is born, and boom, it pops out, and it looks like this. Oh, what a lovely looking baby boy, right? And lo and behold, this same exact organism, oh my goodness, I just cut off his hand. I just destroyed that little baby. It was bad. So there we go, okay. So I take that baby, and maybe 9 months and 3 weeks later, boom, a genetic clone pops out. So these two that I'm connecting here with this red line are genetically identical, also known as clones. Woo! So we can do this with anything. Frankly, we can do this with complex organisms like human beings if we wanted to. We can do it with very not complex organisms like fish if we wanted to, which wouldn't be nearly as interesting, but it certainly has been done. So the bottom line is that the problem with this type of technique is that you don't know what you're getting. Because just like you have no idea what your child's going to look like, what her personality is going to be, how dumb, how fat, how ugly she's going to be, you can predict it to some degree because you can look at the parents and have a sense of it, but you can't be absolutely certain. So while these things are clones of each other, they are not what are called predictable clones. What we would love to do, right, is to take an adult, right? So we take Darren Chang, the handsome devil with a bow tie, and this, look at that. Oh my goodness, what a good-looking man. And we would love to be able to clone him, because the world would be awesome if there were multiple Darren Changs. So what we needed to do was to develop a way to make a genetic clone of an adult. What's the problem with that? Don't forget that adult cells, mature cells, are no longer pluripotent. They've specialized. So if I pick off a skin cell out of Darren Chang and try to make a clone from it, all I'm going to get is a whole pile of Darren Chang skin, which is, I guess, better than nothing. But it's not exactly what we were looking for. All right, so that's the old method of cloning. It's cool, but it's not that cool. We want to do the method of cloning that can give us a second Darren Chang. Bye.